In this video, we'll be talking about errors that can occur when we're trying to measure force using strain gauges. And there's quite a few different ones. For example, our gauge factor. And our gauge factor is something that can change based on our expected gauge factor, like what's written on the packet, to our actual gauge factor. And this can vary a little bit with temperature. And so we've got different things of doing temperature compensation there. For example, using a Wheatstone bridge and using a reference strain gauge there. We've got things of apparent strain that are occurring. We've got sensitivity towards transverse strain, so not the direction that we're moving in, but the other direction that we're moving in when we were looking at this example here before. We've got effects of self-heating. Now, we've got a small amount of current flowing through our strain gauge because it's connected to this Wheatstone bridge. And you've probably experienced before that have some 240 volt wiring and you're drawing a lot of power through it, maybe through an air conditioner or some heavy duty lighting or something like that. That wire will heat up a little bit. It'll become warm. Now, this is happening at a same level, but at a much smaller level with our strain gauges, that if we've got a wire that's got current flowing through it, we can have that wire heating up. Now, if that wire heats up, remember what we had before? We had our resistivity changing with temperature. We can change our resistivity by us actually heating it up as well. And so that's something that we need to think about and compensate for. What about misalignment? When we think our strain gauge is perfectly aligned, but it's just a little bit off. And if it's a little bit off, we're no longer bending perfectly like this. We're kind of bending a bit like a twist here. And so that misalignment can be an issue. And often these alignments are done by hand. You're kind of sticking these things on. So we need to make sure we stick them on reliably and repeatedly. Depending on the thickness of our test piece, if we've got really thin test pieces, we might have them flopping around a whole lot and we might have more noise induced into our strain gauges. Now, our Wheatstone bridge, if we haven't matched our resistors perfectly, might be non-linear. So that might be an issue and might be changing in an undesirable way. We've got that thermocouple effect, so changes occurring with temperature. And if our strain gauges, our reference strain gauge isn't right next to our other strain gauge, or there's some strange way it's being heated differently to our actual strain gauge, we're going to have a mismatch between our reference strain gauge, which is meant to be compensating for temperature, and our actual strain gauge. So there's a few other temperature effects there. We can have errors in our amplification. So often we want to amplify these tiny little voltages to become larger voltages. And we can have errors that are creeping in with noise when we're trying to digitize them, convert that analog voltage to a digital value. Now here there's a corrections table with a whole bunch of different ways that we can correct for a lot of these errors and the sort of magnitude of these errors. For example, 7% when we assume a gauge factor of 2, but our gauge factor is actually something quite different. Now, a lot of these errors are quite small, and so we're talking about tiny little errors there compared to some of our larger errors, for example, with our gauge factor there. So with our gauge factor, for example, rather than assuming a particular value, we can measure our value or calibrate our strain gauge to a certain gauge factor and work out precisely what it is. And that significantly reduces the gauge factor error we've got there. And with our gauge factor, if we have a temperature measurement within our system, we can actually measure our temperature, and using our gauge factor and the temperature dependence of that gauge factor, we can compensate our gauge factor for whatever temperature we've got. So for example, our gauge factor is computed at room temperature, but our strain gauge is operating in a warmer environment of 80 degrees. Well, we can say our gauge factor is plus 0.1% per 10 degrees Celsius. Now, when we've got 80 degrees Celsius, we've got a significant offset that's occurring there. We also have our apparent strain. And so sometimes we've got a significant material mismatch between the material that we're trying to measure and our strain gauge that we're using. For example, if the temperature coefficient for our material is very different to the temperature coefficient for our strain gauge, we might have significant expansion of the material and a different expansion that's being induced into the strain gauge. One of the other significant areas is adhesion, how well we're actually adhering to the material that we're trying to test. Here we have two different strain gauges mounted to a piece of metal, and the one above is mounted with glue and it's really well attached. We don't have any air bubbles in there. We've got a nice smooth contact between our strain gauge and the metal that's underneath. But that one over here, we've used Loctite, and there's actual bubbles that are building up and have occurred underneath the strain gauge, between the strain gauge and the material. Well, when we've got this, we'll have unreliable measurements occurring. And sometimes that strain gauge might be measuring well, but there might be some regions within that strain that aren't measuring well, that aren't well characterized. And these bubbles may increase over time, causing the strain gauge to delaminate and degrade in performance over time as well. So one of the major factors is making sure our materials are nice and clean, and we're adhering using the proper glues, and we're adhering well to the material under test.